Hi, today we will be discussing Lab 4 of Physics 2212, Circuits and Capacitors. In this experiment, we will learn how resistors and capacitors behave by building circuits using the circuit construction kit. We will also predict and compare measurements of current and voltage. The first part of this lab analyzes a simple circuit with two resistors in series. The second part of this lab looks at an RC circuit that contains a resistor, a capacitor, and a light bulb. Before we get into the actual lab, let's look at some of the fundamental physics principles involved. First, the potential difference between 2 points is the current times the resistance. The node rule states that the current entering and exiting a node must be equal. The loop rule says that the voltage drop around a circuit must be 0. Resistors can either be connected in series or in parallel. Resistors in series have an equivalent resistance that's the sum of each individual resistor, and resistors in parallel have an equivalent resistance that is equal to the reciprocal sum of each individual resistor. The RC circuits that we will look at in the second part of the lab have their own set of properties. The potential difference across a capacitor is the charge divided by the capacitance, and capacitors discharge exponentially according to the following equation. Taking the natural log of this equation allows it to be plotted linearly, which we will do later on. The slope of this plot is the negative reciprocal of the time constant Rc, which is when the voltage is 1 over E of its original value. This was the circuit used for the first part of the lab. The two 1.5 volt batteries combine for a total of 3 volts, and the two resistors are 47 ohms and 100 ohms, and since they're connected in series, the total resistance is 147 ohms. Both ammeters measure a current of 0.02 amps, which matches the calculated expected value shown on the left. Reversing the ammeter doesn't change the measurements. When one ammeter is removed and replaced with a voltmeter, the current stops flowing. The voltmeter reads negative 3 volts, which corresponds to the battery's EMF. It's negative because the positive lead is touching the side with less potential. This graph shows the potential differences at different points in the circuit. The potential difference is 0 along any wire segments and the ammeter. It increases by 1.5 volts for each battery, and across each resistor it decreases proportional to the resistance. When an ammeter is connected in parallel with the 100 ohm resistor, the current increases. All of the current only passes through the ammeter because it has less resistance than the resistor itself. The 100 ohm resistor is essentially removed from the circuit so we can act as if there's only a 47 ohm resistor. This gives a current of 0.06 amps, which is calculated on the left. This is the RC circuit that was used in the second part of the lab. The light bulb is on while the battery charges the capacitor, but it dims and turns off as the capacitor becomes fully charged and the current stops flowing. When the battery is removed from the circuit, the capacitor discharges and the light bulb turns on again, but it dims as the capacitor loses charge. While charging, the current flows counterclockwise, and when the 10 ohm bulb is used, it takes 8.57 seconds to charge and 10.29 seconds when the 20 ohm bulb is used. The current reverses direction when discharging and takes 13.02 seconds and 19.65 seconds respectively for each bulb. In this part, we measured the voltage across the capacitor at 1 second intervals for 20 seconds, and then using Excel and these equations, this plot was made. The line of best fit has a slope of negative 0.1667. Taking the negative reciprocal of this gives the time constant of 6, which corresponds to the theoretical value, which is also calculated below. In a real-life circuit, ammeters would have slight internal resistance that would cause small drops in voltage, but this does not happen in the idealized simulator, since all the ammeters have an internal resistance of 0. If we tried to charge a capacitor with no resistor, it would charge instantaneously in an ideal model, such as the simulator, since there's no resistance. But if we used a real capacitor and a real battery, it would take an extremely short non-zero amount of time because all the elements in the circuit would have some internal resistance,